For this section, we'll be talking about complex numbers. Complex numbers are just another type of numbering system. If you've heard of integers, integers are whole numbers that have a positive or negative attached to them, things like -3, +5, -17. Real numbers are any number that you can really think of, so 1.284, pi, 0, things like that. Complex numbers are just another numbering system, but they involve imaginary numbers. So the first thing that we should do is make note of what the imaginary numbers are. So we'll start with a definition for what the imaginary unit is. So the imaginary unit we call I is equal to the square root of -1. So in the past, whenever you've dealt with the square root of a negative number, you've just said that there's no solution. It's impossible to take the square root of a negative number. But now we know that what we really should have been saying is that there is no real solution. There is a complex solution. So whenever you see a negative inside of a square root, that immediately tells you that you are dealing with a complex number. So from here we say that the square root of -a is equal to the square root of a times I. The I is not inside of the square root. You will often see this written as I square root a, but this technically isn't proper notation. We'll get to just in a moment why this isn't technically the correct notation. You should write it the square root of a times I. Okay, so from here, let's go ahead and try an example to simplify this complex number. We have the square root of -36. Well, the first thing that we can do here is take out the negative from our square root. If it helps you in your intermediate steps, you can write it like this. Just make sure in the final step you write it in its proper form. So when we take this negative outside of the square root, we would have I times the square root of 36. And now from here, the square root of 36 gives us 6. So we have I times 6, which simplifies down to 6i. So 6i is the simplified form of the square root of -36. So, again, always make sure that the I is coming at the end of whatever number you have here. It's a notation thing, just like you wouldn't write x2. We know that it should be written 2x. It's the same reason you don't write I6, you write 6i. Alright, so now let's get to the reason why that's important. Well, we have a definition that says the set of complex numbers, which we write as this C with a line through it, have the form A plus BI, such that A and B are in the real numbers. This capital R with a line through it represents the real numbers. And we say A is the real part of the complex number and B is the imaginary part. Notice that it's written BI. We write it in this form, A plus BI, because whenever you get to graphing complex numbers, these values will work the same way as a coordinate point, x comma y. Instead, it will essentially become A comma B. So it is important that you do write it out in this exact form. The real part, then plus or minus the imaginary part immediately after. Okay, so from here, we're going to start going through how to deal with complex numbers the same way we've dealt with real numbers. So to start off with, the basics, addition and subtraction. How do we add or subtract complex numbers? Well, our process says we just combine like terms. Just like the i's were x's. If they were all x's, then you would just combine like terms. It's the same way with complex numbers. Meaning, 5 minus 4i plus negative 2 minus 3i, we will combine the 5 and negative 2 and the negative 4i and negative 3i. So 5 plus negative 2 gives us positive 3. Negative 4i minus 3i gives us minus 7i. And that's it. We have the simplified form of these two complex numbers being added together, just as if we were adding two real numbers, like 5 and negative 4. Okay, so again, notice we wrote the real part, then the imaginary part. It is proper notation, so we can leave it like that. Go ahead and take a moment, pause the video, see if you can't simplify these two complex numbers that are being subtracted. We have negative 3 plus 2i and negative 2 minus 5i. Okay, so the first thing that we need to do here is get rid of this subtraction. We can't start combining like terms until the subtraction is gone, so we will distribute the negative, which gives us negative 3 plus 2i. Note, these parentheses mean nothing because there's nothing in front of them. And then we get plus 2 plus 5i. And from here we combine our like terms. Negative 3 plus 2 gives us negative 1. 2i plus 5i gives us plus 7i. And that is our complex number from what we originally started with. Okay, so from here, we can start talk about multiplying. So the first thing we need to do is introduce a fact that says I squared. What you get when you square the square root of negative 1, well, the square root and the square cancel off, leaving you with just negative 1. So I squared is negative 1. Whenever that comes up in your problem, you just change it to a negative 1. So with that, to multiply complex numbers, we just use the distribution method. Or, if you're more comfortable with it, the box method, or the FOIL method, whichever you prefer. It just means that we are multiplying these just like we've multiplied polynomials in the past. There's no difference. So, first thing that we're going to do is distribute the 7 to the negative 3 and the positive 4i, and then we'll distribute the negative 2i to each of these terms, which gives us 7 times negative 3 is negative 21, 7 times 4i is plus 28i, negative 2i times negative 3 gives us plus 6i, negative 2i times 4i gives us negative 8i squared. Now we start simplifying. So we have negative 21 plus 28i plus 6i gives us 34i. And here, negative 8i squared, well, I squared we said is negative 1. So we get negative 8 times negative 1, that's going to become positive 8. So we have negative 21 plus 34i plus 8. And now we combine our like terms. Negative 21 plus 8 gives us negative 13. Plus 34i. Remember, real part, then imaginary part. And that is simplified. Okay, go ahead, take a moment. We have 5i times 2 minus 3i. Go ahead and pause the video. Try this one out. Okay, so to simplify this one, we're going to take 5i and distribute it to the 2 and negative 3i, which gives us 5i times 2 is 10i. And then 5i times negative 3i is minus 15i squared. I squared, we know, is negative 1. So this becomes negative 15 times negative 1. Negative 15 times negative 1 becomes positive 15. So we get 10i plus 15. But this is not in our complex number notation. We have to switch the order, so we get 15 plus 10i. Since this is a positive 10i, we just add it on at the end. So 15 plus 10i is our simplified answer. All right, so we have a couple more examples with multiplying, and then we can get to division and then exponents. So from here we have a definition that says the conjugate of a plus bi is a minus bi, and vice versa. The conjugate of a minus bi is a plus bi. So the conjugate just means that when you multiply them together, you're essentially going to cancel out a middle term. Think of it very much like the difference of squares formula. So, going to this problem, we have a minus bi times a plus bi. We are multiplying the conjugates together to see what's going to happen, why this definition is important. So, when we distribute this a and distribute this negative bi, we get a times a is a squared. A times bi is plus a bi. Negative bi times a is minus a bi. And negative bi times positive bi is negative b squared I squared. Notice ABI minus ABI will cancel off, leaving us a squared minus b squared times negative 1 instead of I squared. And a negative times a negative gives us a positive b squared. This is a very important formula. Remember, we've been able to factor the difference of two squares, but now we know how to factor the addition of two squares. In the past, this would never factor, but now it does. It factors into two complex numbers, and they are conjugates. So a squared plus b squared factors into a minus bi times a plus bi. All right, so from here, let's go ahead and multiply this out. But the nice thing is, notice 3 minus 5i times 3 plus 5i, these are conjugates. So we don't have to go through this multiplication process. We can immediately use our formula. When you multiply two complex conjugates, you get the real part squared, which is 3, plus the imaginary part squared, which is 5. Just make sure it is in this correct order, 3 minus 5i times 3 plus 5i, or 3 plus 5i times 3 minus 5i. Make sure it's in our complex number notation, and we can immediately just apply the formula. Simplifying, we get 3 squared is 9, plus 5 squared is 25, which just leaves us with 34. So we multiplied two complex numbers together, and we just got a real number. The complex form, the complex part, or the imaginary part that is, canceled off. This technically is still a complex number. Every real number is technically a complex number, because you could technically rewrite this as 34 plus 0i, and it's the same thing. Okay, so from here, let's show why this is important. We want to simplify negative 3 plus 2i over 5 minus 4i. Well, how can we simplify this if we have a complex number in the denominator? We use the complex conjugate. If we multiply the top and bottom of this fraction by 5 plus 4i, then that will leave us with only a real number in the denominator, which we can then simplify. So, always remember, whenever you have a fraction involving complex numbers, multiply the top and bottom by the conjugate of the denominator. So, simplifying this, we have negative 3 plus 2i times 5 plus 4i. I'm going to write that out. All over 5 minus 4i times 5 plus 4i. Well, we know that's just going to become the real part squared, which is 5 squared, plus the imaginary part squared, which is 4 squared. So we'll start distributing. We're going to distribute the negative 3 and distribute the 2i. That gives us negative 3 times 5 is negative 15. Negative 3 times 4i is minus 12i. 2i times 5 is plus 10i. And 2i times 4i is plus 8i squared. And that's all over 5 squared is 25, plus 4 squared is 16. Now we'll start combining like terms. We have negative 15 doesn't have a like term right now, so we'll just copy it back down. Negative 12i plus 10i gives us minus 2i. Plus 8 times I squared is going to become 8 times negative 1. And that's all over 25 plus 16 is 41. 8 times this negative 1, we can simplify to become minus 8 all over 41. And negative 15 minus 8 gives us negative 23 minus 2i over 41. Is this in our complex notation? Well, no, because we have only one term. We need to have two separate terms being added or subtracted. So we need to break this up into two separate fractions. This is going to give us negative 23 over 41 minus 2 over 41i. We always want to write it in the form a plus bi or a minus bi. The I should not be part of this fraction. That's why we write it out of it separately. So negative 23 over 41 minus 2 over 41i is the simplified form of this original complex number that's being divided by another complex number. Go ahead and take a moment, pause the video, see if you can't simplify 1 plus I over 1 minus I. Okay, so going through this, the first thing we should note, is that we need to multiply by the conjugate of the denominator, which is 1 plus I. When we do that, we're going to have to distribute this 1 and then distribute this I. So 1 times 1 will give us 1. 1 times I will give us plus I times 1 will give us plus I again, and I times I will give us plus I squared, and that's all over. Remember, when we multiply conjugates, we only take the real part, which is 1, and square it, and then we add the imaginary part squared. Well, what is the imaginary part? It's the number multiplied to our I, but notice there's nothing there, which means there's technically a 1 there. So, simplifying this, we get 1 plus I is 2I, plus I squared is negative 1, all over 1 squared is 1, plus 1 squared is 1 again. 1 plus negative 1 will cancel off, leaving us with just that 2I in the numerator, over 1 plus 1 is 2, and the 2's will cancel, leaving us with just I. 1 plus I over 1 minus I is just another form for I. Alright, so the last topic we have for this section is dealing with exponents. So when you have an exponent for your I, we've already done a few of these. First of all, let's consider I to the 0 power. Anything to the 0 power, except for 0, is automatically 1. I to the first power, we've already talked about that. That's just the square root of negative 1. That doesn't simplify. It's just I. I to the second power, we said, is negative 1. So what's I to the third power? Well, if we take I to the second power and multiply it by another I, we would get I to the third power. And we know I to the second power is negative 1. So really we have negative 1 times I, which just gives us negative I. So I to the third power is negative I. Now I to the fourth power. If we take that negative I, because we have I cubed times I again as I to the fourth, so if we take that negative I to represent I cubed, we'd get negative I times I. That gives us negative I squared. And negative times I squared is the same thing as negative times negative 1, which is positive 1. So what should I to the fifth be? Well, notice we've just restarted back at the beginning. I to the fourth is the same thing as I to the 0. So what should I to the fifth be? It should be whatever comes after I to the 0, which is I to the first. So I to the fifth is just I. We could prove that very quickly. I to the fifth is really I to the fourth times I. We said I to the fourth is 1, so we get 1 times I, which is just I. So I to the sixth, just to show it very quickly, I to the sixth is now I to the fifth times I. We said I to the fifth is just I, So we get I times I, which is I squared, which we've said before is -1. We are repeating the same 4 values over and over and over again. 1, I, -1, -I. And then it just repeats again. 1, I, -1, -I. 1, I, -1, -I. And it'll just go on forever and ever. So how do we simplify that? Well, we introduce a fact that it says I to the mth power, no matter what m is equal to I to the remainder of m divided by 4. Every time we cycle through 4 of these, we end up getting back to where we started. So if you divide it by 4, your exponent, whatever the remainder is will be what happens when you take away all these cycles of 4. And it will get you back to this original list of 4 possibilities. This is also technically written as I to the m mod 4. This is not something that you need to know, but if you've ever studied modular arithmetic, then this is really what's happening here. So, with that, we have I to the 13th power. We want to simplify it without just running through this list. So we're going to take 13 and divide it by 4. 4 goes into 13 3 times. 3 times 4 gives us 12. When we subtract, 13 minus 12 leaves us with 1. 4 does not go into 1, and there's not a number to bring down, so this is our remainder. So I to the 13th power by this fact is equal to I to the first power, which we know is just I. I to the 13th power is the same thing as I. Okay, take a moment, pause the video, see if you can't find I to the 200th power. Alright, so for I to the 200th power, we're going to take 200 and divide it by 4. 4 goes into 20. It does not go into 2, but it goes into 20 5 times. 5 times 4 is 20. We subtract, which leaves us with 0. We get to bring down that 0. 4 does not go into that 0, but because we brought it down, we say that 4 does not go into it, meaning it goes in 0 times. Whenever you bring down a number, you have to write a number up top. So we don't just leave it at 5, we put a 0 up here. And now 0 times 4 gives us 0. We subtract 0 minus 0 is 0. And now, because there isn't a number to bring down, and 4 does not go into 0, this is our remainder. We have a remainder of 0, so I to the 200th is equal to I to the 0 power, which anything to the 0 power except 0 is 1.